Occasionally I get asked the question, is it possible to go off-grid using solar and batteries in the UK? And my answer has always been no, it would be too impractical and too expensive to do so. And there are other benefits of being on-grid anyway, so I wouldn't really want to be off-grid even if it was possible to do so. But I've never really done the calculation, so I wanted today to go through a plausible calculation just to see how much would it cost to go off grid using just solar and batteries, and is it practical in any shape or form? So yeah, let's go through the process now, and we'll see where we end up. So my starting point with this was our particular system, and could I scale it up in some plausible way to cover our consumption over the whole year. Now, our system is a split east-west array, 3.4 kilowatt peak on each side of the house, so a total of 6.8 kilowatt peak. Now, obviously, east and west split isn't ideal for maximising your total generation. So for the rest of this calculation, I'm going to be assuming we're talking about south-facing panels, and we're going to be doing a large ground-mounted array. But before we get into all of that, let me show you my typical generation. This is a chart I show in my sort of monthly stats videos. If you've seen any of those, you'll be familiar with this. And this is our typical generation pattern. The blue is the prediction from PVGIS, and the green is from last year, and the the green is from last year, and the orange is so far this year up to October, obviously. And you can see that in the summer we generate quite a bit. We generate way more than we need. And in the winter we generate very little, so somewhere in the region of 100-ish. So last December we generated about 62 kilowatt hours. In January this year it was 128 kilowatt hours. So not very much, but let's compare that to our consumption. So this is our consumption for the last 13 months, and again I show this in my stats videos. And you can see that obviously in the winter, so this is January, we consume quite a bit. So this particular January required a fairly heavy heating load, so it was the best part of 1254 kilowatt hours. December was nearly 1100 kilowatt hours. And in the summer, obviously, we use a lot less, down at sort of 300-400 kilowatt hours. But yeah, as you can see, most of this is the heating, so the air-to-air heat pump system. And just to show you what the heating looks like, this was the heating over the last couple of winters. So last year, this is why January was so high in terms of our total monthly consumption, because it was pretty cold, and we used 645 kilowatt hours in January, 500 odd in December. But you can see the typical heating load that we're expecting, this blue shaded area, is around about the 5.5 to 600 kilowatt hours, but it could get as high as 650 thereabouts. So what I did was I took the assumption that what I would need to do in order to go off grid is generate enough power in a typical winter month, December and January, to cover our typical consumption on a bad year. So let's assume that we needed, at the upper end of this shaded area, this plus 1 standard deviation of heating. So 650 odd kilowatt hours of heating. Taking our typical consumption otherwise for the rest of the year, and then seeing if we could match that to with a large solar array. The assumption being that if we were able to cover our consumption in the winter months for a typical, a whole month in the winter, we could generate enough kilowatt hours in 1 month to cover the total consumption in 1 month. Now, obviously, there are variations day to day. I'll cover that in a little bit later. But the basic requirements are we need to generate at least as much as we're consuming in a given month. And obviously, generation varies from 1 year to the next. You can see the plus and minus 1 standard deviation bar here. So what I wanted to do was make sure that in a bad year, if we consumed 1 standard deviation extra worth of consumption because of a cold month, but we also generated 1 standard deviation less than a typical year, that would be a pretty bad combination, but something that could plausibly happen. So therefore, we'd need enough generation even in a bad year to cover a bad year's worth of consumption. Hopefully that makes some sort of sense. So my first step was to go to PVGIS, which is the tool I use to generate this blue shaded area here, the estimate for our system, and I created a fictitious ground-mounted array somewhere in Gloucestershire. And through a little bit of trial and error, I managed to calculate that I would need an installed capacity of solar panels of about 39.6 kilowatts. So about 40 kilowatt peak array. And because we are aiming to cover our use in winter, I actually tilted the panels at 70 degrees. So really very steep because obviously the sun is much lower in the winter. And if you tilt your panels a little bit more towards the horizon, then you're going to pick up more of that winter sun. So I put these numbers in here, south facing, obviously azimuth of 0 here, and that gave me this plot here for the generation month to month. Now you can see that we're generating about 1550 kilowatt hours in December and about 1700 kilowatt hours in January. You'd normally expect if you were to optimize the slope for complete generation throughout the year, it would be about 35 degrees. In fact, let's do that now. Let's put 35 degrees in here and visualize the results. You get a much more generation in the summer, but you get less generation in the winter. So now you can see we're only down at 1257 kilowatt hours in December, but putting this up to 70 and clicking visualize, you can see that that jumps up to 1550. So we get a little bit more generation in the winter by tilting those panels. So that's what I did, and that means that obviously in the summer we're generating less, but that's fine because we don't need as much consumption in the summer anyway. So it's really the winter that we're aiming to cover in this particular scenario. So now, of course, it's spreadsheet time. So I took the data from PVGIS, and it actually gives you not only the expected generation each month. So you can see this is the 1550 odd kilowatt hours in December, but it also gives you a standard deviation. In other words, how much it should vary typically from one year to the next for a given December. Now, I then took one standard deviation away from the expected to give me a generation on a bad year of about 1216 kilowatt hours in this particular example, and that matches neatly with the assumed consumption in a bad year again. So assuming we would need a little bit more heating than normal, so we assumed 1200 kilowatt hours consumption, and that would match with the 1200 kilowatt hours of generation in a bad year. So a bad year of heating, a bad year of generation should just about cover from one for one whole month's worth of living in our particular house using our particular consumption. So I've covered over some of the screen here, and I'll show you why in a minute. But basically, what I wanted to do was take this array of 39.6 kilowatt peak south-facing array, a slope of 70 degrees, and see in practical terms, what does that mean? So you can see the chart here is what I was talking about before. We're matching our winter consumption with the amount of generation, but in the summer we're generating way more than we need. So we're going to ignore all of this extra blue generation here that we don't need for now. I'll come back to that in a minute. But let's start costing up the array that would give us this pattern of generation based on the assumptions that I've made. So I'm going to move this little grey rectangle down very slowly to reveal bit by bit the numbers. So these are the figures I assumed for the panels. So I'm assuming that you could get a pretty decent panel generating 450 watts. I know you can get probably slightly more powerful ones than that, sort of commercial sized ones, and maybe that's a better way of doing things, but let's, for sake of argument, say 450 watts per panel, peak generation, 88 panels, that means, so that gives us the 39.6 kilowatt peak array, and I'm assuming that each panel cost about £50. So if you look on various wholesaler websites, you're probably looking at something around 60 or 70 pounds for a panel of that sort of generation. And I'm assuming that maybe you could get a bulk, a pallet or something, and that would help bring the cost down a little bit. So I'm being pretty generous and assuming you could get a panel of that sort of output for about 50 quid. So 88 panels multiplied by £50 is a total of £4,400 for that particular set of panels. Now, here's an interesting fact about solar panels, when you ground mount them, obviously they need to be tilted, and I've assumed a tilt of 70 degrees, obviously, as I mentioned earlier. But that means that they will cast quite a long shadow. So therefore, how much area would you need to set aside for your array if you had a very steep set of panels in nice neat rows? So let me show you what I mean. This is a good illustration of what I'm talking about. You can see these. This is a ground-mounted system, and they're tilted at probably about the optimum, sort of 35, 40 degrees, something like that. But you can see they're casting quite a long shadow at this point. The sun seems to be a little bit lower in the sky. You can tell it's not quite at its peak. But you see how much these rows of panels need to be separated from each other in order to not shade each other. So this row here would shade this row here if the sun was low, for example. And of course, the steeper you tilt the panels and the lower the sun is in the sky, the further you need to space these apart. So I'm assuming, and I've done a little bit of back of the envelope trigonometry, and I'm assuming that given the height of these panels, you would need to separate them by about 3.5 times as much as the panels are high in order for them to not shade each other too much in the winter, which means that the amount of area covered by an array like this would be about 3.5 times the area of the panels themselves. So let's go back to the spreadsheet and see what that means. So each panel is about 2 meters squared, so multiplying that by 3.5 means that each panel would cover effectively a ground area of about 7 meters squared, and therefore multiplying 88 panels by 7 meters squared would give a total area required of about 616 square meters. So that's essentially, a field. You need your own field to install this sort of system in order to give you enough power to cover your needs for a typical winter's month. But obviously, that's assuming that you can generate about what you need each day. However, that is not always the case, and let me show you why. So this is the generation plot for December last year for our system. And obviously this is much smaller than the array that I'm proposing that we would need to go off grid, but you can see the variation from day to day. Sometimes we're generating more than 4 kilowatt hours in a day, but sometimes it's as low as less than half a kilowatt hour a day. So you would need some way of bridging the gap between reasonable generation days like these and these poor generation days here, like these, for example. So let's say your typical average requirement is somewhere in the middle here. So when you're generating more than you need, you're filling up your batteries, and then that sort of sees you through the dull days when you don't have enough generation to cover your needs for that one particular day. So I've made the assumption that we're going to need about 3 days worth of consumption of battery capacity in order to see us through dull periods. Now, realistically, you might expect that you could get a week like we've had early November this year in the UK, where we've had essentially a whole week of really poor generation. So you might find there are times when you don't generate enough to cover you through even 3 days, but that's another discussion. But as a plausible assumption, let's assume that 3 days is okay for most situations. Right, so let's assume that we need 3 days of battery capacity, and our maximum consumption per day is about 46 kilowatt hours. So multiplying those two together gives us a required battery capacity of about 140 kilowatt hours. Now, how much would you expect to pay for that level of capacity? Well, from looking around the internet at various wholesalers and other stuff, I think the best pounds per kilowatt hour you could plausibly expect is about £200 per kilowatt hour of battery capacity. Obviously, most domestic systems are probably a fair bit more than that, but £200 is probably about the best you could expect. You might get a little bit lower than that, but that doesn't seem unreasonable. So let's multiply 200 with 139 kilowatt hours, and that gives us a grand total of battery capacity of £27,700. Now, here's the thing, that is considerably more than the cost of the array. So there are 2 plausible ways you could reduce the cost of this, but at the expense of less flexibility, shall we say. So you could reduce the amount of battery capacity that you need. So say only 2 days or 1 day. So let's drop that to 2 days worth. That drops it a fair bit down to 18,400. But in order to counter that, you would probably need more solar panels. So you'd probably need to bump this up a fair bit more to make sure that you could generate a little bit more on those dull days and hopefully last you through a little bit further. So that would push up the cost of the array, but also the amount of area that you would need. So if you had a really, really big field, you might actually want to increase your array way beyond what you would need, and that would mean that you could get less battery. But let's stick with my assumptions here for now and assume that we've got 3 days worth of capacity and an array that's about the right size for 1 month's worth of generation. So let's carry on with the calculation and see where it goes. So obviously we need some sort of inverter to convert that power from the array into usable power for the home and the batteries and all that. And now I had a look around again, and an inverter that would give you enough power to hook up to a 40 kilowatt peak solar array, you're talking probably £3,000-ish. So this is basically a commercial scale inverter. I don't know how plausible that is for a domestic situation. I don't know whether that would require some sort of grid connection because it's expecting you to be exporting or not. I don't really know. Again, I'm being sort of generous here and assuming that £3,000 is plausible. You might find that it would be significantly more than that if you needed sort of more lower rated inverters for a domestic setting. It's not something I'm particularly an expert in any way. So yeah, you can let me know in the comments if you think £3,000 is at all reasonable. It's kind of irrelevant at this point. I'll show you why in a second. We also need, of course, some sort of ground mounting system. So I basically plucked a number out of the air because it was very difficult for me to find sort of realistic numbers for this. But from what I could tell, £10,000 may or may not be a reasonable value for all of the equipment that you need to actually install the system in your field. There seems to be all sorts of bits and bobs required, and adding it all up was not something I really fancied doing. So I more or less plucked an answer out of the air. £10,000, so basically double what it costs to actually buy the panels themselves. Maybe this is wildly overblown, I don't know, but again, it's more or less irrelevant because if you add up all of that stuff, the cost of the equipment is pretty much about 45 grand. So if the mounting system cost 5 grand, it's still 40 grand total. So still loads and loads of money, and that's assuming you do all of the work yourself, that you're not getting somebody in to do the installation for you, because I'm sure that would add at least another 10 or 20,000 pounds to the install cost. So yeah, this is literally just the cost of the equipment. Now that is obviously extremely expensive. My system for reference cost me £14,000, so £14,000, and that has it generates almost enough for me to get through the full year, and my bills are very close to zero. I spent about £240 for a 12-month period for my my total bill last year. So I'm pretty pleased with that. I would like it to be zero, and plausibly I could get it to zero if I added a few more panels to my north-facing roof, which may or may not happen at some point in the future. Watch this space. But that is not the only disadvantage. The cost of the install is obviously extremely high, but there's another factor that you might want to consider if you were wanting to go off-grid, and that's you will miss out on all of the export payments that you could get if you were connected to the grid and exporting all of this lovely excess that you've got here. So all of this, wherever the blue line is above the red line in this chart, is excess solar that you can't use. There's nothing you can do with it. It would basically, your inverter would basically limit the power to the point where you're not exceeding what you're consuming, and all of that excess generation would just get wasted. It wouldn't go anywhere. Your panels would be derated to the point where they're not generating as much. They'd only just cover the red amount here. So that means you're missing out on all of this possible export payments. Now, let's say, for sake of argument, I know this isn't a massive array. I doubt you'd probably be able to. This is essentially a commercial scale array. But if you were connected to the grid and you were able to get the typical export rate of 15 pence per kilowatt hour, for the sake of argument, that's the Octopus outgoing rate, you could plausibly have this situation where you're missing out on all of this export, which combined with the export rate of 15 pence would give you pretty sizable income actually for across the year. Now if I just pull this chart down a little bit, you'll see I've added up the totals here, and you could be missing out on up to £4,000 a year of export payments by not connecting to the grid. So yeah, that was incredible to me that not only would it cost you best part of £45,000 to install this, you could have paid it off in 10 or 11 years if you were connected to the grid anyway. Yeah, there you go. So I thought that was a fun little thought experiment just to see how plausible it was for us to go off grid. It's absolutely not going to happen. We don't have a garden even remotely big enough to have a ground mounted system sufficiently sized to cover our winter needs. And it would be far too expensive to get it installed anyway, and we'd miss out on all the lovely export payments in the summer when we're generating more than we can consume. Yeah, I'm sure there are some of you out there who would love to go off grid, and I don't blame you. It's an appealing proposition, but for us, it's not going to happen. But if you found that interesting and you're not already subscribed, please hit that subscribe button for more of this sort of silly nonsense that I do when I bring out the spreadsheets. But for now, thanks very much for watching. I'll catch you in the next one.